Vai agora lá no YouTube ver se começou lá, eles liberou a chave. Bom, pessoal, nós estamos tendo problemas técnicos com o áudio do Davu e estamos tentando solucionar aqui. E assim que solucionar, nós damos um retorno para vocês. Bom, pessoal, nós estamos tendo problemas técnicos com o áudio do Davu.
Hi, my friend.
E estamos tentando solucionar aqui. E assim que solucionar, nós damos um retorno para vocês. Bom, pessoal, nós estamos... e estamos tentando solucionar aqui. E assim que solucionar, nós damos um retorno para vocês. Bom, pessoal, nós estamos... Até minha caixinha de som aqui do fundo da mesa caiu já. Deixa eu ver como que tá aqui a transmissão no YouTube.
No YouTube tá tudo ok, tá transmitindo.
Tá transmitindo, né? Vamos ter que... Vou fechar o áudio.
Também no YouTube, só falta o Davu.
Vou pegar essa aba aqui e jogar. O que tá falando aí?
Nossa, tem alguém no chat agora.
Jean, só ir excluir o que esse spam tá mandando aí no chat.
Tem como banir essa pessoa, não?
Removi lá.
Tá bem.
Cadê o Dabu? In Portuguese now, all right?
Ariel, poderia apresentar ele.
Sim. Pessoal, então vou fazer a apresentação rapidamente aqui em português, a gente atrasou um pouco. O Davu é meu amigo já há alguns tempos, ele fez doutorado comigo na Bélgica. Então, Davu Nasser Esfahani, Ele hoje está morando no Irã, trabalha lá com materiais bidimensionais e vai fazer uma apresentação para nós aqui hoje. Tivemos um pequeno atraso aqui, mas sem nenhum problema, não vai ter uma perca, então teremos uma apresentação bem interessante. Agora eu vou falar rapidamente aqui em inglês e depois a gente vai e fala. Hi, my friends, Davu make PhD in Belgium with me. Years ago, Mr. Davu, you have
yes.
around the 40 minutes for a presentation.
Okay.
Right?
I try to fill it in very efficient way.
Okay.
I do my best.
With you now.
Okay. Thank you so much for inviting me to your meeting. And sorry about the delay. It took a little bit of time to figure out how to solve the problem. And today I'm going to talk about non-adiabatic transitions at touching points. Normally, non-adiabatic transitions have been investigated for gap systems, but we are going to talk about non-adiabatic transition at touching points. So the system is gapless. The outline of my talk is as follows. So I start to talk about a little bit of non-adiabatic transitions, linear crossing problem, and Landau-Zener tunneling. Then I will explain a little bit about optical lattices and how we can, how people have succeeded to implement these Dirac cones in optical lattices. Then I will talk about fidelity susceptibility, and instead of linear derivation, derivation, I will explain how higher order derivation may change the result. And finally, I will show you a little bit of numerical simulations about transition probability. The simplest, in terms of non-adiabatic transitions, the simplest model that people have employed for explaining some observation in atomic collision problems is Landau-Zener Hamiltonian. So I made a mistake here. So this delta is equal to this delta 2. So we should drop out this 2 subscripts. So you can see there is a linear crossing. There is a linear crossing here between lambda and minus lambda. And there is a finite coupling between these two levels, which results in opening of a gap in the model. So we have this linear crossing. Then due to this delta, we have we have this opening of the gap in the spectrum of the system, with the gap is equal to 2 delta. So this model also have been employed for time-dependent problems. Zener used a time-dependent lambda, which is a linear function of the time, and they have Landau and Zener found the transition probability between the ground state and the excited state being equal to exponential of minus p delta square over c. So you can see that when delta becomes zero, the PLZ, the transition probability to excited state, becomes equal to 1. So this is kind of trivial results. If we have this linear crossing, if we have a linear crossing like this, and there is no gap between two states, if we start from here, we end up with an state here in plus infinity. So the transition to excited state becomes equal to 1. So it is very trivial result of Landau-Zenner formula. So then the question is that when there is a non-linearity here in a gapless model, when there is some linearity in the Hamiltonian, what would happen to the transition probability? Excuse me, I should change my slide to another one. I included another slide in between, so but I don't have it here. I can't find it right now. So, okay, I don't have, I had another slide in between, but I don't have it right now. So the question is that if we have a linear crossing, I will explain it right here. So the question is that if we have a linear crossing where the delta is equal to 0, so we have this transition probability being equal to 1. So the question is that if we have some higher order terms in the Hamiltonian, would it affect the transition probability as touching point? The question, this question got our attention when we encountered with some papers that they try to explain the transition probability between ground state and excited state in a system with two Dirac cones. Here you can see we have two Dirac cones here. If I back here, the generic form of Hamiltonian which could produce a couple of Dirac points in the spectrum of the system is this kind of Hamiltonian with an energy dispersion equal to this one. And if delta is less than 0, this Hamiltonian will produce for us two Dirac points at py equal to 0 and px equal to plus minus square root of 2m multiplied by delta, absolute value of delta. The spectrum of the schematic of the spectrum is depicted here. So you see there is two Dirac points here, and people, and if you look at the spectrum, and if we have some intersection of this energy surface with some plane in parallel to the plane consists of E and Px. So we have finite Py, and if we have this intersection, you can see we have these contours of the energy. The Py is not equal to 0 in these cases, and we can show that these contours at lower and upper part of the spectrum could be approximated with two subsequent Landau-Zener Hamiltonians. So if we start from some ground state here, we encountered with this a transition probability from this state to this one, and if the speed of derivation is so large that there is a complete transition from the ground state here to the excited state here, and if we continue here, we would have a transition probability from excited state to the ground state. So we have two subsequent non-adiabatic transitions which could be explained based on Landau-Zener formula, which is called a Skutelberg formula. So the two subsequent Landau-Zener transitions could be explained based on Skutelberg transition probability. Then the question is, so far we have been talking about gapped models. So the spectrum is gapless, but the actual model we use for explaining the transition probability is still gapped. So the Py is not equal to 0. This is the case most people have been looking at so far in optical lattice experiments and so on. Then there is another schematics that could explain for you a little bit easier. So this case is Py equal to 0. When we are away from Py equal to 0, we have these two opening of these two gaps. So actually we have two linear crossings, subsequent linear crossings, that there is an avoided crossing at each of these two touching points. So the spectrum right now, the spectrum that people have considered is still gapped. Then our question is that if we pass through if we pass through these 2 points, then what would happen? I have explained the problem in a compact way here. So what would happen if one passed through the touching points where Py is equal to 0 in a non-adiabatic way? If we consider a spectrum being linear around Dirac cones, that this is an approximation that often people use. So all of us have been encountering this linear approximation around touching point. Then the transition probability must be equal to 1 at each touching point. This means that if we try to pass through these two touching points, so if we consider a linear crossing like what we consider for Landau-Zener with delta equal to 0, so we normally see that these two states does not perturb each other. So we have a transition probability equal to 1 for this process. The process we try to pass through the first touching point, and for the second touching point we could have the same thing. However, I will show you that this is not the case, at least for some kind of Hamiltonians. There are Hamiltonians that there is some certain quadratic terms in the Hamiltonian that does not allow such conclusion, that we have the transition probability to excited state being equal to 1. So this is not the conclusion. This is not something that we could say when there is certain type of quadratic terms in our Hamiltonian. So before starting actual result that we have got so far, let's start with a little bit of a little bit of technical tools we are going to employ for our proof. So we have a two-level system which is explained based on a Hamiltonian, which is dependent on lambda, and actually we are going to derive the Hamiltonian with some time-dependent lambda, which is equal to some c, the speed of derivation, multiplied by t. Then one can represent psi at each instance of the evolved psi. I mean, so we start from some psi 0, and we evolve psi. So at each instance of time, we can represent psi as a linear combination of instantaneous eigenstates of the Hamiltonian, which I show it as n function of lambda t, a ket of n as function of lambda t. So n is equal to 1 or 2. So what these kets are instantaneous eigenstates of a Hamiltonian. This means that at each instant of time, we diagonalize the Hamiltonian, we extract the energies and eigenstates. So we try to write the evolved side based on these instantaneous eigenstates. Then if we try to represent the time dependent Hamiltonian based on this instantaneous eigenstate, we end up with this set of equations for these coefficients. So you see, we have this Cn tile. That Cn tile is defined in this way. What is important here is the fact that we have a coupling between the states, which is a multiplication of the pace of the derivation of the system, and the other part, which is only dependent on the properties of the system, the properties of the Hamiltonian of the system, but it is not dependent on the way we derive the system. Everything here is dependent on time through the lambda. So this system is dependent on lambda only. So then, because lambda is dependent on t, this part also is time dependent. So if we look at this equation, we see that this part couples the adiabatic states, and as long as this adiabatic coupling is large, then we have larger transition probability, and if it is small, we are near the adiabatic regime. So as long as this coupling is large, the non-adiabacity of the system is more pronounced with constant pace of the derivation. So we have two systems, the pace of the derivation is the same. As long as this coupling is larger, the non-adiabatic transition is stronger. So if people have looked at this part as adiabatic coupling, but also it is directly related to this fidelity susceptibility. The fidelity susceptibility is a measure for the change of the ground state, or if we are talking about fidelity susceptibility of an excited state, the change of excited state as function of the external parameter. And this term in our equation is actually equal to the square of the square root of fidelity susceptibility. So this guy is equal to square root of fidelity susceptibility, or this guy squared, this guy squared is the fidelity susceptibility. As long as the fidelity susceptibility is large, the change of ground state or excited state as function of external parameter is larger. This means that we need to drive the system slower to remain in the ground state, or the non-adiabatic transition is more pronounced. So this is the tool we are going to use to explain the difference, to explain how higher order terms could change the scenario for the transition probability. So first of all, let's look at the Landau-Zenner model with delta equal to 0. So we have this very simple Hamiltonian. This is only a linear crossing, which chi is equal to 0. This means that if I start from so this means that there is no perturbation between the states, and if I start from an state here, I end up with an state here without change of character. So if I start from 0, sorry, 1, 0 here, I end up with 1, 0 here as excited state. So the transition probability is equal to 1. Because there is no change, there is no perturbation between the states. So this is a special case, and this is also consistent with Landau-Zenner tunneling. When delta is equal to 0, the Landau-Zenner tunneling shows a PLZ being equal to 1. Now let's look at another problem, which there is some other terms in the Hamiltonian, but the system is still gapless. So if we look at to this kind of Hamiltonian, this kind of Hamiltonians are Hamiltonians that could happen in P-wave superconductors between the trivial and topological phase in the boundary of the trivial and topological phase of a P-wave superconductor. So the gap is closed in this regime, and so we have this kind of Hamiltonian actually. The dispersion relation of this Hamiltonian is equal to this formula, which we have a touching point at lambda equal to 0. Actually, this is not touching point. This is a crossing point when lambda is very small, but okay, we call it touching point. If I try to calculate the fidelity susceptibility for this system, you can see I end up with this expression for chi lambda, and the limit of chi when lambda goes to 0 is equal to 1 over 4 m squared delta squared. This means that different from the trivial case of linear crossing, in this case, even so, when the lambda is very small, this lambda square are much smaller than lambda, and we end up with actually a linear crossing if we think about it in a naive way. But you can see, no matter how close we are to the touching point in this case, chi lambda is not equal to 0. So it acquires a finite value. This means that in any vicinity of touching point, the two states are perturbed by each other, and there is no way to approximate the Hamiltonian with simple linear crossing by just dropping out these two terms when we are very close to touching point. I explained here in more explicit way. So if I come back here, one may tempted to just ignore these two terms, because these two terms have square. We have a square of lambda in these diagonal terms, and we have linear lambda in off-diagonal terms. So maybe someone says, okay, when lambda is very small, these two terms could be ignored in comparison to the other two. So I can approximate the Hamiltonian with kind of 0, 0, lambda delta, as long as I am close enough to the touching point. So for this case, I end up with chi tilde of lambda being equal to 0 when lambda goes to 0. However, we show to you, I showed you that if I calculate chi directly by using this Hamiltonian without any approximation, I mean without ignoring this lambda squared, so I end up with non-zero chi at lambda equal to 0. So this is the main result of this research. So we show to you that there are certain type of Hamiltonians with a square with some quadratic terms, which cannot be reduced to a linear one. In at least if we are going to look at the system from the point of view of non-adiabatic transitions. So then we tried to see the effect of larger order terms in diagonal part of the Hamiltonian. So we wrote the diagonal part of Hamiltonian as a polynomial, G lambda, which is expanded up to nth order, and we again calculated chi, and we ended up with chi in this way. So you can see if I take the limit that lambda being equal to 0, only a square a2, the amplitude of the quadratic term in G lambda contributes in the fidelity susceptibility chi lambda at the touching point or near touching point. So I can neglect higher order terms, but I cannot neglect the amplitude of quadratic terms. So you see, I can neglect higher order terms than 2, but I should not, I must not really neglect the quadratic term. So how it could, how this argument could be related to what I explained to you as implementation of Dirac points in the optical lattice experiments, that they produce sort of such Dirac cones, two isolated Dirac cones with a linear dispersion close enough to the touching points, and how our arguments are related to this type of problems. So you know, when we talk about the Dirac points, we are talking about linear terms at touching point. But keeping only linear terms at touching points is only an approximation. So we expand. If I come back here, so normally we write a tight binding model for this Dirac type of graphene-like Hamiltonians around some k points. So we have this SK as this complicated function of kx and ky, and normally people expand sk around k point and k prime point, and finally they end up with a linear approximation around k point. So normally you work with this part. The low energy Hamiltonian for the Dirac Hamiltonian could be approximated with this only linear terms. However, if we try to keep higher order terms, here if we keep second order terms, so we expand, actually we expand this sk up to quadratic term, quadratic approximation, and we end up with this Hamiltonian, with this approximated Hamiltonian. And if we come back, to the Hamiltonian, to the model here, so if we pass through the touching point, Dirac points, we need to set Qy equal to 0. So I'm going to do that here. So I am going to set Qy being equal to 0, and instead of Qx, I put some lambda as an external parameter. So if I do that for this Hamiltonian, you see that I end up with such kind of Hamiltonian, which it has lambda and lambda squared in off-diagonal part of the matrix. The dispersion relation for this system also is gapless, and with the touching point or crossing point at lambda equal to 0. Then if I use this gauge transformation for this Hamiltonian, I end up with this kind of Hamiltonian, which is actually the same, exactly the same as the Hamiltonian of P-wave superconductor. I mean that P-wave type. When I say P-wave superconductor, I mean at the boundary of trivial and topological phase of the P-wave superconductor. So you see, it has exactly the same form. So this fidelity susceptibility does not become to 0 as at lambda when lambda goes to 0. So this means that this linear approximation for the Dirac points doesn't work when we are going to look at non-adiabatic transition at the touching point. If I throw out these two quadratic terms, you already know that I would end up with a transition probability being equal to 1. But when chi is not equal to 0, this means that the transition probability also is not equal to 1. It would be different. It would be less than 1. So we are going to show you some numerical simulations to better understand how the transition probability changes. So we also try to look at some other Hamiltonians which these diagonal terms have larger order. So in these cases, in agreement with our analysis that only quadratic terms are important at touching point, you can see that I can calculate the fidelity susceptibility for this gapless model, and if I plot the fidelity susceptibility for this system, you can see that at the touching point, the only system that doesn't have a non-zero fidelity susceptibility. The only, sorry, someone called me. I just rejected him. I don't know if I interrupt, if the presentation was interrupted or not.
It was.
Okay. So
now we can see.
Okay, I'm going to repeat that part. So we try to see
No, this part we already saw the VU.
Okay. So I'm going to next slide. So if I plot the fidelity susceptibility here, if I try to plot against lambda, you can see that the only Hamiltonian that it has non-zero fidelity susceptibility close enough to the touching point is the one which n is equal to 2. The p-wave superconductor, p-wave-like superconductor Hamiltonian. If I include larger orders, n equal to 3, n equal to 4, you can see in all of these cases, the fidelity susceptibility near the touching point becomes very small, and at touching point, it is actually equal to 0. So for these cases, when I have only when I have order 3 or 4 or order whatever larger than 2, I can actually approximate the Hamiltonian with a simple crossing Hamiltonian. So this means that I can neglect these two guys as long as n is larger than 2. So when n is larger than 2, I can approximate the true Hamiltonian with only these two parts. But if n is equal to 2, I cannot neglect quadratic terms because the fidelity susceptibility is not equal to 0. It doesn't approach to 0, and it takes its maximum at lambda equal to 0. So the Hamiltonians, which have certain type of quadratic terms, are not reducible to linear crossing. But if we have larger orders, we can reduce the Hamiltonian to a linear crossing. We also looked at gapped models, which we drop this lambda here from the gapless model, and we end up with a gapped model. What we found is that the fidelity susceptibility of these two are very similar to each other. Even so, the transition probability behave quite differently. Again, you see for n equal to 1, for the gapped model, for n equal to 1, we have maximum fidelity susceptibility. Actually, n equal to 1 for gapped models is nothing but the Landau-Zenner problem. So if I set n equal to 1, so I drop n, this is nothing but the Landau-Zenner problem. Therefore, for the Landau-Zenner problem, the fidelity susceptibility of Landau-Zenner problem is very similar to the fidelity susceptibility of p-wave superconductor. But it doesn't guarantee that the transition probability behave in the same way, because we have this band structure that affects the transition probability through the dynamical phases that are accumulated through the evolution into coefficients C/N that I showed you in the I think fourth slide. But we have this relation for the fidelity susceptibility. The fidelity susceptibility of a gapped model with an order n minus 1 is equal to gapless model with order n. So let's look at transition to some numerical simulations about the transition probability. So if we start from some phi instantaneous eigenstate at -infinity, this minus means the ground state. So if I start from the ground state of the Hamiltonian, whatever Hamiltonian, at -infinity, and if I evolve this wave function, so psi zero is equal to phi, ground state phi as -infinity, then I will evolve psi 0 to +infinity. Then what I calculate as transition probability is the projection of psi +infinity into psi plus at infinity again. So this psi plus is excited state at +infinity. Then a square of this guy is the transition probability. This is what we report as transition probability here. So if I look at Landau-Zener problem, this is the transition probability for Landau-Zener problem. You can see that the transition probability becomes smaller as long as delta 2 squared is larger. So this is completely in agreement. This numerical simulations is completely in agreement with this PLZ is equal to delta squared P delta squared over C. So when we increase the speed of derivation, also the transition probability drops. So this means that we are approaching the adiabatic regime. Then if I look at when I look at the transition probability for gapless model with n, the order of n is equal to 2, which is the same as the Hamiltonian of the P-wave superconductor, we end up with a very different scenario. And the most important one is that as long as I increase the speed of derivation from 0.2 to 1, the transition probability will be suppressed. So this means that for this Hamiltonian, when I try to derive the system with a linear derivation, then as long as I increase the speed of derivation, the ground state probability becomes larger. So maybe it is an interesting result also. So you derive the system faster, you end up with a smaller transition probability or larger ground state probability. And if I compare GP to the gapless model and the gap model with n equal to 2, and or gapless model with n equal to 4, you can also see the same behavior. So here for GL4, if I increase the speed of derivation, so I increase speed of derivation in this way, then the transition probability decreases also. So we got the same results. The same result as GL2, but the way this transition happens in GL4 is quite different from GL2, because for GL2 we have only one peak in fidelity susceptibility. So there is one passage happens through the non-adiabatic transition, but when we have n larger than 2, for example, n equal to 4, we have two passages. One passage from -infinity to 0, so we have a large transition probability here, and we then if we evolve the resulting wave function to +infinity, we have another another area with large adiabatic coupling or chi, which results in some transition probability again. So actually we are working on that still, because at least for gapped models, we have shown, I didn't present the results here because it makes the presentation too large, but we have shown that when we have these two peaks in gapped models, we have interference between between wave function resulting from the passage through this one and this one. So it is a little bit difficult to explain without mathematical formulation. Okay, formulation is simple, but it is a little bit difficult to explain it. But we have kind of superposition of wave function between these two states. So this superposition of wave function passing from -infinity to 0 and from 0 to +infinity, we see kind of superposition which results in an oscillatory behavior of transition probability as function of gap. However, we don't see such a oscillatory behavior here, and you can see some one step of oscillation here for GP2 also here. But when we increase the order of n in gap model, we end up with more oscillation, which these oscillations are the result of some kind of superposition, some invariance for the evolution between -infinity to 0 and from 0 to +infinity. Such oscillation does not exist for gapless model in any order if we try to plot the transition probability as a function of delta. And the reason is that the invariance doesn't happen for gapless models because when we pass through the touching point, the energies change their sign, and the dynamical phase fade out between an evolution from -infinity to 0 and from 0 to +infinity. This is another result that we have not presented here, but I just wanted to mention. Okay, I am going to finish my presentation. I would be happy if you have any question to answer any questions of yours. Thank you so much for hearing my presentation.
Thank you, Mr. Davu. We have just time for one question. I think about the graphene is the replace the silicon in the next years. Do you think about it?
Sorry, about the graphene, this second order.
The graphene, the replace the silicon.
Yes. Okay, that case is a little bit, because the silicon is actually, oh yes, silicon also is gapless, and why may see the same behavior? Because this is not what I presented here is not restricted to graphene, and this is a graphene-like dispersion. So any graphene-like dispersion could have the same properties. So silicon could have, if someone tries to do some experiments with silicon. I don't know if it is possible, but he or she may get the same result.
All right. Mister, we have our time is very, very short. Again, we thank you very much for our presentation here. And in our opportunity, we can in Brazil, right? Again, thank you very much for a presentation.
Thank you so much for hearing me. Thank you so much for inviting me. I am really happy to see you.
We're very happy staying in our events, and thank you very much.
Thank you so much. Thank you so much.
See you.
See you, Davu.
See you
Thank
soon.
you.
See you soon.
Bye.
Bye. See you soon.